welcome. Thanks for coming. So my name is Valentina. I am with PLUMgrid. PLUMgrid is a software-defined network provider for OpenStack clouds. So we have a network solution in software that plugs into OpenStack as part of Neutron and helps customers build scalable, high-performance solutions. Since I'm the first one of two covering kind of the same topic, I'm going to do a little bit of intro on OpenStack networking, and hopefully it's going to help frame the discussion for both PLUMgrid and Midokura and get some of the kind of basic constructs out there. I've been with PLUMgrid for 3+ years, so kind of since the beginning of it, and I was at Nicira and Cisco before that. So I've been lucky enough to been working with OpenStack and software-defined networks since the very, very beginning of it. And I've been able to work with a lot of the early customers and early adopters of both OpenStack and SDN technologies. So happy to share some of what I've learned over the years with you all here. So I want to just kind of start from why is networking such a big deal? And if you guys are familiar with the super user survey that OpenStack releases every 6 months right before the summit, and you go check back out the one in November, Neutron was the #1 concern for any user of OpenStack. And the reason being that really networking, it's kind of the junction of any cloud design. So when I work with customers, they tell me, should I start with an SDN layer? Should I go with, a kind of default OVS implementation? Should I just, go and configure VLANs in my physical network infrastructure? And I was just talking with some of you earlier on. And the answer is really, look, when you start, you can go with anything. If you start with 5 servers, you're going to be fine just, picking whatever solution out there. But, what's important is when you go and look at the long-term plan for your infrastructure and you look at how it's going to scale past these 5 servers, how it's going to perform when you start putting more interesting use cases on top of it, that's where architectural choices become important. And if you're not familiar with Neutron, Neutron is the network component for OpenStack. And it was introduced with the Folsom release, so not from the very, very beginning of times of OpenStack. And it was created really to satisfy the use case of network as a service. So giving the ability to both cloud operators and tenants to log into OpenStack as a dashboard and self-service provision networks. And this was going past the implementation that was kind of the basic implementation that was available through Nova networks and providing more rich network functionalities for customers to use. Now, Neutron was from the very beginning built as a modular architecture. So the beauty of this is if you start with OpenStack, Neutron gives you this abstraction layer. And it gives you the ability to define networks, connect these networks with routers, define kind of the private IP space that each of your tenants is going to use, define how that interconnects with the external world. And all that it's nicely and clean defined for you. And it's completely independent of the underlying implementation of the actual network solution. So what this means is that Neutron doesn't really provide the functionality. It provides an API layer, an abstraction layer, that enables, again, the cloud and the tenant operators to consume these network resources on demand. And then all these definitions of networks get passed back to the backend implementation. And this is where usually there is quite a bit of confusion when I talk with customers. They ask me, oh, so is Neutron actually OVS? And is Neutron actually VLANs? Is Neutron doing overlays? The answer is Neutron is just this very thin layer that presents this abstraction of networking, subnets, routers, IP spaces that can be consumed by users of a cloud, and enables a bunch of vendors, a very broad ecosystem of vendors, to then plug in their solution. I want to help you visualize this concept here by showing one possible implementation of Neutron. So one choice that you can make is, hey, I already have an infrastructure in place. I don't want to go crazy. I don't want to introduce an SDN layer. I don't know what you guys are talking about. I just want to go and stay with what I know. So you can certainly use Neutron to just talk VLANs, speak VLANs. So you can use Neutron to go and configure VLANs in your actual physical infrastructure and use VLANs as the isolation mechanism for multi-tenancy. One of the principles of Neutron is really these multi-tenant environments, right? So VLANs can be a fine example of multi-tenancy if you don't hit any of the limitations in terms of scalability, ability to provision more rich and complex networks abstractions on top of what the physical network can give you. So this is kind of flavor number one. Flavor number two, which is where we're going to be spending most of the time tonight, it's the overlay model. So the overlay model, differently from VLANs, doesn't really go and configure anything on the physical infrastructure. So the overlay model relies on some software component that you have inside each compute node in OpenStack. And through this software component, which we're going to talk more about, can be OVS, can be what PLUMgrid uses, which is called the IO Visor. That software component will enable the creation of a tunnel infrastructure. And this tunnel infrastructure will very beautifully give you the ability to define these multi-tenant networks on top of a shared physical infrastructure. So all the isolation, the ability to define your own private network will come built on top of this overlay. Overlays have beautiful properties in terms of scalability. The physical network is not exposed to virtual machines, IPs, and MAC addresses. So from a scalability perspective, you don't consume MAC and IP table spaces in the physical gear, which is great. You can have, because you're fully isolated in this tunneling, through this tunneling infrastructure, you can give tenants their own private IP spaces. They can define any form of logical network that they want on top of this. And this is really what, kind of the benefit of the overlay. And the physical infrastructure becomes very simple, very stable. It doesn't see lots of changes and reconfigurations. And all the multi-tenancy and self-service provision comes in this virtual layer that sits on top of the physical network. Now, tonight we're talking a little bit about NFV and the ability to virtualize all the network functions that are available as physical components in the network. And so I want to use this one picture here. I'm going to take it slow and try not to run over all of you here. This picture here to explain where some of the network functions can actually live within an OpenStack deployment. And again, what is key here as a takeaway is that the actual implementation depends on which vendor and which solution you're going to pick. Right? So depending on what each networking solution can do, the network functions that you're virtualizing can live within the kernel. So if you're having either a kernel module or some form of kernel-based software that you're running, components you're running there, or it can be as user space components. And usually what we see as example is in kernel you have switching, very, very commonly. Some vendors have routing. Some others have more advanced functions. That's where you have in kernel. So that's where you get the best performance. So VMs will be able to just go from user space down to kernel space and use these functions. You can use functionality that are sitting in the user space. So that's kind of a model number two. When VMs have to consume these network functions, they will airpin from the kernel down up to this user space, consume these services, and then down again into the kernel, out into the physical fabric. So your performance and ability to scale out, it's a little less optimal. And then kind of the third model is when you have what in OpenStack is usually referred to as a network node, which is nothing but a server or a set of servers that it's sitting somewhere in your infrastructure that is hosting the more advanced functionality. This is kind of the worst case scenario. That's when you're going to have to send the VM traffic through the kernel, out into the physical fabric, all the way up to your network node and consume this functionality. So really, when you go and pick a solution, the choice that you make is going to dictate where this functionality are going to be made available to your tenants. And I'll obviously talk a little more about how PLUMgrid satisfies this and how and where we provide these functions. But this is a great kind of general slide for you to have a feel for where they could sit in a deployment. Why does this matter? It's really that when you start looking at how things will scale out, when you go past that 5 initial nodes, 10 initial nodes, if you have a suboptimal placement of these functions, you're going to have to start wondering about how to optimize your design and how to make it highly available and how to make it get a better performance. And the common theme through what PLUMgrid and Midokura do is really to make a lot of these functions distributed. So you'll see a lot of this theme throughout the presentations there. So what you can see when you have a suboptimal placement is that the VM packet flows will be very different depending on which functionality that VM needs. So let's say that 2 VMs need just layer 2 connectivity. They'll be able to go through kind of the bridge directly within the server, right? And as we were discussing earlier, if they need to access more advanced functions, they'll be punted up to the network nodes providing this functionality. So again, if you start with few servers, life is great. If you start having 50, 500, or 1,000, these network nodes will start to right away become bottlenecks, and the placement of the agents becomes critical. So really key is understanding what's the right architecture for your deployment and for your environment. So I want to give you just a feel for what we do and and where we come in and help with some of the more advanced use cases and some of these NFV-like deployments that are happening on top of OpenStack. So PLUMgrid, as I said earlier, it's a software-only solution. We are optimized for OpenStack. We integrate with all the major distributions. So we have fully automated deployments with all the major distribution. And what we do that it's very unique is we have the concept of virtual domains. Now, think about a virtual domain like an Amazon kind of VPC environment, that it's dedicated to a tenant, to an application, to a user. A virtual domain, it's a lot more flexible and rich than the OpenStack abstractions. So I'll touch upon a couple of the more advanced use cases that we see customers using the virtual domains for. But the very basic use for it is to be the backend of OpenStack Neutron, OpenStack Networking. So we take the API call that comes from the dashboard or from the API, and we map it into our concept of bridging and routing, NAT, security policies, and isolation. What we do that it's very unique to the solution is that all the feature and functionality that are represented in purple here, so bridging, routing, security, DHCP, DNS, NAT, PVLAN bridging, and a bunch of other things that we have, are all implemented absolutely 100% distributed. So anytime you design a network and you map it on top of PLUMgrid, all the functionality you need are going to be always available in kernel. And by such, they're going to just scale out automatically as you add more servers and more VMs to the problem. And the data plane that we have, it's quite unique, and it's fully extensible at runtime. So it gives you kind of the best platform to deploy all sort of feature and functionality there. Now, when we work with customers, especially those that are looking at NFV use cases or some of our kind of traditional OpenStack customers that are building environments where they want to have layer 4 to 7 services being integrated as part of an OpenStack deployment, we see the use cases for what we call service insertion architecture. So we see the use for what we call service insertion architecture. Now, service insertion architecture is the ability to augment a virtual domain that PLUMgrid provides with all the distributed functionality with these orange components that you see here. And these orange components are third-party appliances, firewalls, load balancers, VPN, that can be service stitched and inserted in a topology that it's provided by PLUMgrid in an automated, simple way. And the beauty of the model is that we can stitch into this topology virtual appliances. We can stitch physical appliances or slices of physical appliances. We can also stitch third-party components that are deployed as containers, being LXC or Docker. And so again, you can see, especially if you start looking at NFV kind of use cases, this gives you the ability to define the network infrastructure, define the service, and chain in all your functions in a very easy to consume way. And this gets, again, provisioned through OpenStack if that's the platform that you're using. And for some of the advanced use cases, some of our customers take advantage of our API layer to be able to automate these more advanced services that you have here. So one last thing that I want to cover is just to give you a glimpse kind of behind the covers of how does all of this get implemented. There's 3 components to the product that we have. The first component is what we call the IOVisor Edge. So the IOVisor is our kernel module. As we said, we don't leverage OVS. We have a much more extensible, programmable framework at the data plane level. And the IOVisor Edge is the one that provides connectivity to the virtual machines and provides the ability to distribute the virtual domains definition across all the servers. The same IOVisor code can also run as a gateway. If you're familiar with overlay networks, there's always a construct of a gateway. A gateway is the on-off ramp of traffic from the overlay network into the legacy infrastructure. And we have the ability to support both software gateways in an active mode, as well as hardware gateways that come from our partners. Again, in an active mode. And again, the gateway is kind of the termination point of VXLAN, and it's also how we onboard and provide virtual domains that can have not just virtual machines, but physical workloads, as well as other form of workloads like containers, if that's what you want to use. And the third piece of the puzzle is the PLUMgrid director, which is quite different from the traditional SDN controllers. It's deployed as a cluster, so you have 3 machines that are providing kind of the brain functionality of the system. And it's the one that it's in charge of talking and interacting with the API layer of OpenStack. And the director is where all the control planes of all the network functions that you have for each virtual domain run. It has lots of interesting high availability tools that are built into it. Some of you were asking me earlier on if we were going to talk about the new release that we just announced last week. And I'm not going to go into all the nitty-gritty features. But something that it's important to just notice is that as we see more and more OpenStack adoption, we see really the need for operational tools and visibility and monitoring and in just the ability to take a pulse of what is happening in the OpenStack network. So something that we're doing more and more is to build tools into whether it's the overall cluster, the overall deployment of PLUMgrid, what we call a zone, or into individual components to help customers just very quickly and effectively troubleshoot the environment. So we definitely see the bar raising in terms of conversation moving from I want layer 2 and layer 3, fantastic. I want some advanced features, and now I want the ability to deploy, operate, troubleshoot these environments in an effective and easy way. I know I'm running out of time, so I'm going to just show you this one last slide as a summary, and then take any questions. So somebody earlier on was asking me, why would I go with Nova Networks, or why would I go with kind of default Neutron, and why would I consider PLUMgrid? And really, it's all a matter of understanding what is your use case, what type of scenarios you want to build on top of OpenStack. And we see that as kind of a ramp in terms of, if you have limited scale, you're probably going to be fine with, as I said earlier, kind of whatever implementation it's out there. If you want to start scaling out, if you want to have kind of the best level of performance, looking at a more distributed architecture that it's capable of satisfying a broad array of layer 2 to 4 functionality right in the kernel, it's a great asset for your architecture moving forward. And again, based on what our customers are telling us, the ability to automate the creation of the entire infrastructure from layer 2 onward, and the ability to, again, in an automated way, insert any arbitrary function really opens up for a lot of great use cases moving forward. All right. This was a quick presentation, but I hope it was helpful for you to get a feel for kind of OpenStack networking and some of the architectural challenges that we see there, and how we at PLUMgrid help solving some of those. We just as an FYI, we just recently launched this program called Ignition. And I encourage any of you that it's new to OpenStack or new to OpenStack networking to go check it out. It's a sandbox environment with OpenStack and PLUMgrid. We spin it up for you. No commitment. It's free. You get a bunch of training associated to it. A test plan that you can follow, and it's a great way just to get started with the whole OpenStack thing, and get to play with SDN and Neutron. So that's available at our website. If there's any question, sure.
So you mentioned that you're supporting OpenStack APIs, and then you have an extended set of APIs for extended functionality. OpenStack really has this whole embedded workflow of how it does its provisioning and so forth. How do you see the interleaving of the API extensions with?
Yeah, so the question was around API extensions and how that plays within the overall OpenStack workflow. And that's an excellent question, and it's something that we see with 100% of our customers. 100% of our customers leverage some form of functionality some functionality is outside of kind of the core API. And the way they do it is they usually, again, nobody will go through the dashboard, right? Let's assume that in production, everybody's going to just automate through API. And what they do is they just script the core to the core API for whatever it's supported through OpenStack, and then additionally script everything that it's coming directly from PLUMgrid. Now, the good thing of OpenStack and kind of the database model is that there's objects that are owned by OpenStack, and the workflow there, it's very clear. If they're owned by OpenStack, it always comes from the OpenStack API, and PLUMgrid, the only reason why you would use PLUMgrid API or the dashboard that we have is for troubleshooting. For these, for example, tools that I was telling you about, to get better, more advanced stats on each network port and what packets are doing. But it's read-only. So these objects are owned by OpenStack. Objects that are owned by PLUMgrid, those get configured through the API. So it's the object ownership that dictates where the configuration comes from.
Thank you.
Any other questions? Sure.
So you said the control plane is centralized. I think you said at the directors, right?
Yes.
So when you deploy L4 through L7 services or L2 through L7 services, are those at the edge? Are those at the directors, and are they stateful?
So the question was around control plane on the director and L4 to 7 services. So let's take it a step back. So any PLUMgrid virtual network function, so it's one of the purple ones, those are PLUMgrid functions. They're fully distributed, and the way they work is the control plane instance for that VNF will live on the director with the HA and redundancy that's built into it, and then that control plane will have a correspondence of, let's say, 10 data planes or 100 data planes or whatever many. It's a span of that tenant network. And that's one class of VNFs. The other class of VNFs are the orange ones. So the orange ones are partner VNFs, and they're not distributed. Okay? So what happens there is you can deploy them. There's a lot of variety of ways. You can deploy a single virtual appliance per tenant, per virtual domain, for example. And that usually sits on either edge or a service rack. So you're going to have to airpin the traffic through that, right? It can be a physical appliance. It can be container, so it can be sitting somewhere on a compute node. The model is quite different if it's a purple VNF versus an orange VNF. What it's consistent for the user is you can automate the complete provisioning of your virtual domain and the virtual domain topology and do all the service stitching automatically.
Okay, the purple ones, do you have like functions, the firewall function?
We have security groups that it's implemented not using IP tables, so it has much better performance. So these are the VNFs that we support.
Okay. And these ones you said are distributed?
All 100% distributed, yes.
And they're
no, there's no user space component. There's no controller. You never pan packets user space, never pan packets to controller.
So if it's distributed across, like, say, I have 3 hosts, if something goes out one firewall, like one host?
So security groups and security policies are stateless.
Right. Okay. Okay.
Yeah, we can talk more offline if you have a specific question there. Yeah. Any other question?
You mentioned the
IO visor, yes.
That's faster than the OVS, or what the improvements are there?
Absolutely. Otherwise, we wouldn't have built it. So the question is the IO visor faster than OVS? Yes. So there is a few architectural differences. And I mentioned earlier, what it's important to understand is that OVS was built from the get-go as an open flow data plane. So it's really, flow-based, and anytime there's a flow miss, you're going to pan packets up to user space, to the user space component there. And the other key thing there is that it's kind of a hard-coded data plane. What it means is that it was designed to support layer 2 functionalities and some layer 3 functionalities, and some tunneling was added on. But every time you need to add new functions, you're going to have to rebuild the component and go and update your kernel and go and redeploy your hypervisor. The IO visor was built from the get-go to be a fully extensible and loadable at runtime environment. What it means is that the way to envision is as the IO visor is kind of an empty box at the beginning of time. It doesn't have any functionality. And based on what VMs need, we're dynamically loading kind of a layer 2 snippet of code, a layer 3 snippet of code, a NAT snippet of code. And we can connect them and service chain them together dynamically to bring you the virtual domains. And because it's not flow-based, the architecture is completely different. We don't have to pan packets up, and we have very different, again, kind of underlying architecture there. So we certainly see better performance in a lot of scenarios, and we've spent quite a bit of time on that. Yes?
So there's some IO visor code that you have up on
Yes.
GitHub. Is that close to what you ship in production? Do you maintain that? Or?
So the question was, there's some IO visor code in GitHub. Absolutely. So we recently upstreamed and open sourced the data plane component. We use eBPF, which is extended Berkeley packet filter, and we brought it back to the community. We're seeing great adoption of it across the board. There's lots of very interesting use cases that are being built, and it's 100% what we have in the product.
Right.
All right. Thanks a lot. I hope I didn't use too much time.
Thank you very much.